Thank you all. You can hear me just fine, right? Yeah. I'm gonna try to like woo, so that everybody hears me. All right, so the forensics of RSAs first. Thanks to Riaz and the Tech Tank folks for putting this together. Such a cool event. It's always been. This is not my first time, so. And also thanks to the Points Office for lending us the space. This is really cool. We're going to talk about RSCs, React Server Components, specifically the forensics of it. So this is an interesting lens in looking at RSCs. We're going to see some nifty, fine data. I see a lot of beers over there. I'm going to give you a quick tip. This talk is going to be much more fun if you have beer. Just joking, but yeah. Thanks for coming all. My name is Lazar Nikolov. I'm a developer advocate here at Sentry, based in performance, focused on web performance, based in Toronto. And I say Toronto, of course. And yeah, I like to learn new things. I'm a nerd. I like to teach them to the folks in my communities, and occasionally I want to give talks, just like this one. I run a YouTube channel at Nikolov Lazar. This is something that I started doing this year, and I love it. And yeah, creatures.sh is one of my communities. If you want, join it, it's chill. It's like 500 people, much smaller than the Tech Tank one. So cool. All right, let's dive in. What are the RSCs, or React Server Components? So we're talking about a new architecture in React ecosystem, a new innovation that leverages the good parts of client-side rendering and server-side rendering. It leverages streaming HTML, and we'll actually see how the Next.js server streams the HTML. And it does that so it sends all of the website's data, not all of them, but like sends the data as fast as possible to the browser, so the browser can start painting pixels while the rest of the data is being obtained. Really cool, because it's good for performance. And it does that so while it minimizes the bundle size. And we'll see how how they achieve that. Before we dive into RSCs and the whole RSCs thingy, I thought let's talk about the evolution of React rendering first, and then we'll see why, or like what was the reason RSCs exist in the first place. So this is going to be the React rendering, not website rendering. All right, so we're starting around 2013 maybe, not the 90s. So the first React application was client-side rendered. Right, we built our application in React using classes, good old days. So what we did, we bundled the whole application into one bundle. We put it either on our servers or our CDNs. And we just make the server or CDN, just throw it to the browser, hoping that it will know how to handle it. And for the most part, the browsers can handle that, but it wasn't without any drawbacks. So when we're talking about client-side rendered applications, we're talking about the server sending HTML to the browser that is pretty much empty. It's just one div with an ID of app inside and a whole bunch of JavaScript that is about to be downloaded and executed. And then we're going to start seeing some things pop up on the screen, right? At least the app shell. And then that JavaScript makes other fetch requests to fetch the actual data that we need to display on the page. Cool, right? That was fine for the most part. But because we're sending an empty HTML, we're actually hurting our SEO, because the data doesn't have the initial payload doesn't have any data. So search engine crawlers needed to be optimized to invoke JavaScript in order to get the data so that they can crawl and index the page accordingly. But that basically knocked off a few points from our SEO score because we didn't send any data, right? And then we were like, OK, we sent all of this JavaScript with no HTML virtually to the client. The client then fetches all the data. So the client still needs to make an API request, go back to the server, the request that actually served the website, fetch all the data, and return it back. So like we're making two trips, right? Give me the site. OK, now give me the data. So we started rendering our applications on the server. So instead of the browser, the client, being responsible for generating the HTML and populating the screen. We cut that, we moved that step to the server. So now when users are visiting our application, the server will generate all that initial HTML and send it back to the browser. So the first thing that the browser sees is rich HTML. Now we got some data, and the browser can start to render it immediately. So that was cool. That solved the SEO issue that we had. We had better ranking sites because we're not putting the search engine crawlers to work. But that now means that we have to have servers. We can't have an SSR application on a CDN. CDN is cheaper, server is more expensive. But yeah, we solved one thing, but we lost one. Still fine. Thinking about what we could optimize next from this point, we are rendering the website on every request. And for example, the static elements like the footer, the header, and the site navigation, and the app shell itself, we keep re-rendering that to HTML as well, right? So we were like, okay, when I say we mean like the developer community overall, right? The world. So we were like, okay, let's figure out how we can optimize a bunch of these steps so we don't need to do unnecessary steps to generate these pages. So we branched into two different rendering modes. That's SSG and ISR. First, the SSG came. Well, that stands for static site generated, right? We took SSR and the capabilities of servers generating HTML, and we did that in our pipelines. When we run npm run build, we get static HTML. We take that, we throw that to a CDN. We're back on a CDN now, cheaper. That's always good. And we don't need to re-render that HTML on every request. It's just much faster. One thing I didn't mention is that when we had SSR, the time to first byte score suffered a nice hit. Why is that? Because every time we visit a website, the server needs to generate the whole HTML from zero, right? And it takes time. And time to first byte means when is the first byte received from the server since starting the requests. So knowing Web Vitals, if the time to first byte is higher, all the other Web Vitals will just follow. Where in this case with SSG, we practically have just the latency as like time to first byte because there's nothing of processing happening on the server. But this means that if we want to make just a simple change, we still need to rebuild the whole website, right? So that's not good as well. It's, you know, we can't say, okay, we're happy now. So we need to do something about it. And then we came up with ISR, and not we. This is, I think, Next.js more specifically. ISR stands for incremental static regeneration, and it is a hybrid between SSG, meaning that we're generating the static HTML at build time. We're uploading that to a server, but we still have a server so that the pages that have data changing, like the blog page or I don't know, any page that might have some new data, they get regenerated after a specific time frame, right? So we have a server. We're not on CDNs. We serve static content initially. So when we run npm run build, we get that bundle, we mark it as v1, and we serve v1. When a user lands on our page, we serve v1 to the user, but we trigger a separate process in the background so we can see if we need to generate v2. If we have v2, then we'll just continue serving that. There's a window where users are looking at stale data. So that's not good as well. So what can we optimize after this point? Yeah, that is pretty much RSCs. If you noticed, up until this point, we basically juggled between client-side rendered, server-side rendered, and we did SSG, and then we did ISR, and we keep, I'm going to say hypothetically, we keep refactoring our applications to get these benefits, but we actually lost these things in order to get these, so it's been a trade-off. It's been a trade-off, and I think that's why the RSCs as an implementation, as a rendering strategy or an architecture is like the next logical steps in that progression that we saw, because it allows us to pick all of these specific rendering strategies per component. So if we want to have the footer dynamic for some reason, let's just make it dynamic for the fun of it, we can, right? We can regenerate the footer every time we have a request coming in. But we know that we're going to make that static, right? So we're not going to waste processing power to regenerate everything that doesn't need regeneration, but we're going to mark the ones that we need, right? And that way, we actually reduce the amount of JavaScript that is being sent to the browser or downloaded by the browser and executed by the browser, because not everything needs to be hydrated, not everything needs to be run on the client. And we'll see how that happens. Our SEO is improved because we have still the capability of serving static content that doesn't need regeneration. And we basically don't have any trade-offs at this point, and that's not the ones that I mentioned. So yeah, we're still allowed to maintain the interactive dynamism that users expect from a website in 2024, right? So I think it's been like almost 2 years since React marked RSCs as stable, and people are looking into adopting RSCs for reals about this time. So in times like these, when you're refactoring or adapting a new architecture, new application, monitoring is invaluable. It still has some rough edges, RSCs. So you want to keep an eye on your user experience. You want to keep an eye on your performance. You want to keep an eye on your errors. And because I work at Sentry, I should talk to you about Sentry. So yeah, Sentry offers performance monitoring and error monitoring to all of you. I'm going to say all of you because we have too many SDKs for me as a DevRel to support. So all of you. It tracks your releases. It tracks your errors and your performance. And it tells you when your app is doing what it's not supposed to do. So you can track your releases before, during, and after refactoring, for example, into RSCs. So you know whether you made a good choice implementing RSCs, or you simply jumped the hype train that the RSCs is on. So yeah, check out Sentry, sentry.io/for/Next.js. You can see what Sentry does for your Next.js apps. Just replace Next.js with any other framework, and you'll see what it does for that framework. But we're fair source. That means you can pull the code, you can put it on your own servers, run it for free, pay for Hetzner. Or you can start a free account on Sentry.io, the managed one, and then grow it as your team or application grows. It's basically free to get started. So yeah, check it out. It's really cool. But let's get into the anatomy now. RSCs as a technology, as like an architecture, introduces two new component types. And those are server components and client components. And the difference between these two aren't functional. They function the same. The difference is where they get executed, when they get executed, and what gets sent to the browser. So the client components, and there's like a really, I hope you can see that from all the way from behind, but yeah, they're the good old components that we know since 2013, 2014. Their code gets shipped to the browser, right? That means they have access to the browser APIs. When I say code, I mean JavaScript. That means they have access to browser APIs. If they have access to browser APIs, that means they can handle interactions. If they handle interactions, we learned that lesson from SSR, we need to hydrate. So that means we have one step to do before we actually make them interactive. It's a big detail right there. And the only thing that we need to do to keep building client components nowadays is just to add that use client directive at the top as the first line. No comments before that. That has to be the first line. It's not the 17th line, it's the first line. It's just my IDE. So that is the only thing that you need to know. Use client, put it at the top. Now it's a client component. That means Everything that's inside gets shipped to the browser. All right? Now we have server components, and these are the new thing. Okay? They are executed exclusively on the server. Nothing gets sent to the browser, nothing of their code. And they're also executed in one go. And what does that mean? We can easily avoid fetch waterfalls because we know you have conditional rendering, you have data fetches to fetch the data, and that's your recipe for fetch waterfalls, and that's bad for performance. But in server components case, we actually don't care about that because they get executed in one go. Okay? Their code doesn't get shipped to the browser, only the output of their code does. And by output, I mean it's a function, invoke it, get the output, that gets sent to the browser, not the actual code, right? That means no JavaScript is being sent because the only thing that this function returns is JSX, which will get converted into HTML. So there's no JavaScript. That means there's no interactions. But that also means that there's no hydration. So the browser has fewer things to do in order to display this component as opposed to a client component, right? That means it's safe to use server technologies. I know some people might frown when they see await db.product inside of a React component, but it's there for like a demonstration purpose. Safe to use server technologies because, again, we'll just invoke that function. We don't care what it uses. We'll get the output as like HTML, and we'll just throw the HTML to the browser. The browser doesn't know where that HTML, how that HTML got generated. Is it using Prisma or not, right? So safe to use server technologies, and also large dependencies do not contribute to bundle size. You can pull the whole Lodash library if you want, right? You're just going to ship a bunch of HTML elements to the browser. Lodash or not, it's still going to be static HTML. So that's a big win. There's definitely a big win. And there is no use server in this case. You might have seen use server coming up in React and Next.js topics online. That's a different thing. Those are called server actions, which are basically RPCs in Next.js land. So for server components, we don't need to do anything. By default, it's a server component. We don't need to mark it. It's a server component. It's going to get executed, and the results will be sent to the browser. OK, these two types of components, they have their own special relationship. It's not complicated. This is how a tree, a view hierarchy looks like when we're working with RSCs. By default, as I mentioned, every component in React RSCs mode is a server component. And that's on purpose. That's on purpose, so we don't bother with marking or forgetting to mark a component as a server component. We just want that performance benefits out of the box. Everything is a server component unless we have to handle interactions or use browser APIs like the media or local storage, etc. In those cases, what the React team suggests us we do is to isolate that into its own component, mark that one as a client component, and then have access to the browser APIs. But everything else stays as server components, right? This basically tells us that if we were to draw this as like a tree, the full hierarchy, the client components would be the leaves of the trees, right? We only isolate specific specific APIs into client components, so we can only send that to the browser, but the rest that stays on the server. And it doesn't mean that server components are SSR. They work in a different way, but we can talk about it later. So yeah, this is basically the recommended approach when building your or adapting RSCs. Everything is a server component unless you really need to use APIs from the browser or handle on-click interactions. Handling interactions doesn't mean a form with an action, or it doesn't mean a link. Okay, those are like HTML native interactions. I'm just talking about JavaScript interactions. When you need to send JavaScript to the browser, that's when you create a client component. And one thing you should have in mind is if you explicitly import a server component, without the marking at the top, right? A server component into a client component, you won't get an error. I believe there's already an ESLint plugin to let you know that you're making a mistake, but React will treat that server component as a client component. It will automatically convert it for you. It won't actually throw an error or even a warning. It'll just convert it to a client component, and it'll try to send it to the browser. So what this means, the outcome can be different. If you have a fetch in the server component, the fetch is going to work, right? Next.js, they do patch the fetch API, but let's just say it works on both on the server and the client, so no issues there. You're sending another API request from the server side to a third-party service that you're using, and you're sending the API. Well, guess what? The API key is now in the browser, and everyone can see it. So you can leak sensitive information just by importing that server component into a client component. So that's a big no-no. A better case scenario than that is you're going to get an error because the browser does not know what DB is, nor it can pull in Prisma and instantiate a connection to your database. So it'll just throw you an error because it doesn't have the library. Or if none of those things are happening, this is the best case scenario in the scenario where you're making a mistake. It's just going to be no APIs, no databases, no sensitive libraries or information. It'll just send the code, the JavaScript to display that component to the browser. You won't leak anything, but you're just sending unnecessary JavaScript to the browser, which you can avoid if you just don't import that one. But if you really need to have a server component in the subtree of a client component, you can just pass it through the props. That way, it'll stay as a server component. That's everything that you need to know in terms of how server components and client components coexist into one React and RC's project. So this is going to be tough to see, but I'm going to talk through the whole thing. And this is basically what happens when we visit a page that is using RSCs to render itself. So starting from the top left, we have a blank page. The client makes a GET request to the index page. And then we have, as actors, we have Next.js and React. This part right here is just zoomed in this block right here. Okay? So when the browser makes the request, the Next.js server on the server side will find the route server component, and every page, every route in Next.js must be a server component, so it will try to find that. And it will send it to React that lives on the server, not on the browser, that lives on the server. It'll ask it to render the server component along with its all subtree. So what React does, it's going to go component by component. And based on the type of the component that it encounters, it's going to do three different things. Before I talk about that, it's important to note that Next.js does some pre-rendering optimization. So some of the server components might already be pre-built. Okay? Now let's see. If React on the server encounters a client component, it will prepare client component instructions. Basically instructions for the browser on how to load, render, and also hydrate that client component, because we need hydration in client components for them to work, right? And that is being done in a form of an RSC's payload. We'll see a payload example later, but imagine that there's just like a JSON object that describes how this component is hydrated, how to load it, etc., and all of its dependencies. And it just returns it back to Next.js, the server. If it encounters a suspended server component, and that is the component, for example, that we saw await DB, it's asynchronous. We do database calls or API calls inside. We're fetching some data. That is an asynchronous server component. In that case, when we're using asynchronous server components, we're most likely either using a suspense boundary with a fallback definition, or we have a loading.js file or tsx file in Next.js if we're using Next.js. Both cases define what is the fallback for this component going to be. And by fallback, I mean a little spinner in most cases, or a skeleton, right? That is the fallback. So we have two definitions of how asynchronous or suspended components look like. One is the actual component with the data from the database or third-party service, and the other definition is how the skeleton or fallback is going to look like. So when React encounters a suspended component, it'll just take the fallback value, return that as the HTML for that component, but it will invoke the component in the background and keep it there. And then if it encounters a server component that doesn't actually fetch any data, it's just there. It's most likely pre-rendered by during build time by Next.js. It already has the HTML, so it'll just return that HTML and do nothing about it. Okay? So with that approach, React will go through all of the components in the component tree and return everything to Next.js. So Next.js has this whole HTML block and a bunch of RSS payloads that give instructions to the browser what to do at what time, right? It streams that initial HTML to the browser. It streams it. It doesn't just say return and that's it for the HTTP call. It streams it back to the browser, and we'll see how that streaming looks like as well. So what the browser will do is we have initial HTML, we have some RSS payload that tell us how to fetch additional CSS files or other JS modules and fonts and assets and resources and stuff. So the browser will start to render what it has at the moment, which is what I like to call the page shell, right? We have all the static elements, we have the styling with the CSS and everything. While we're fetching the data for, I don't know, the data table that's like smack in the middle of the website, we can still render the page and interact with it. We don't need hydration for HTML native interactions. If I want to, as a user, if I want to navigate away from this screen and not wait for the data to load, I can. But if this was an traditional server-side rendered app, I'm going to have to wait for the data just to realize that I'm not on the page that I want to be. Okay? So at this point, the browser has enough HTML to start rendering the web page. And in the places of suspended server components, it just loads the fallback element, the spinner or the skeleton or whatever we define for them. As these suspended components finish loading, the Next.js server has an interesting way to tell the browser to keep the connection open. As these finish, they report back to Next.js with the static HTML generated with the whole data and also the RSS payload. And Next.js just streams that additionally to the browser, right? So in that way, as components finish loading, the browser just replaces a spinner with a data element, and then another one, and then another one, and like progressively will render the whole web page. And at that point, at the end, we'll just basically have the whole page loaded and ready to be used. But we started to show data much earlier in that process. So that is how Next.js and actually React utilizes streaming to send data back to the browser as early as possible without having to having the browser wait for the whole data. We're going to look at the streaming and what the browser actually sees from a data standpoint. But let's talk about the payload first. I believe this is the third iteration. Up until this point, the React team changed this like 3 times already. Might also change another few 3 times. So it's not important that you become experts at payloads and how to read them. It's just I made these slides just so you can see what it is, what it does, just to be aware of as a what the payload is as a communication device. So it is a special data format. It used to be JSON, now it's not anymore. It's a special data format that looks like JSON, and it represents instructions that the server generates, but the browser performs, right? It's basically how the server tells the browser what to do at what time, okay? It includes references to resources and files, which you can see it in the HL payloads. This is like a payload per line. So HL, I think these are called hints. This is undocumented. I had to like dig through GitHub issues and stuff like that to realize what is going on in with the payload. But HL, I think, stands for like hints, and they tell the browser what resource it needs to pull. So if the browser receives an HL payload with layout.css, that means it needs to make a network to the server, so it pulls in that layout.css file and load it up, right? That is the instruction. It also contains instructions on how to load JS files, client components, or any libraries that are used in the page, and those are called I. I have no idea what I stands for. As I mentioned, it's undocumented, but instruction, right? And as you can see here, we're pulling from like node modules. There's the global arrow.jsx that Sentry adds. There's a source components, clear card.js. This is most likely a client component if we're sending its JavaScript. So that's basically the I payload. And also the rendered HTML from the static server components, the client components, placeholders. We are sending the JavaScript, but Next.js also sends a placeholder with instructions on how to hydrate it. I don't know why it does that, but it does that. So client component placeholders are part of the RSC's payload. And any props that are passed from the server components to client components, they're also part of the $ payloads right here. So this is how the server communicates with the browser in the lifespan of hitting enter in the URL bar up until fully loading the web page. These like 3 types of payloads are enough to communicate everything. Pull this resource at this time or load this JavaScript module, and there we go. We have the whole page ready. Okay, that's the RSC's payload. So we're going to look at something. We're going to look at the text file that I generated using the command at the top, curl-d, that's a D, curl-d --row on localhost 3000. I did this on my dev server because I don't want any obfuscation. And I saved everything in a chunked response.txt file to see what the browser actually receives. Okay, at the top, I zoomed in. Okay, so I hope you can see this at the bottom. You think that I was gonna let you read about that? Yeah, this is heavy. I did this in Mozilla, and they were like, we can't read anything. So at the top we have the headers, and these are the response headers. What the headers that the browser received, and pay attention to the last one. Transfer encoding set to chunked. This is a crucial one. This tells the browser that this transaction is not going to be like a single data transfer. It's not going to be like, here's the data, that's it, and close the connection. This header keeps the connection open. So even though the browser receives some HTML, some data, it won't actually close it after the first initial data, right? That keeps the line open, so that's how we stream to the that's how we stream from the server to the client. It's not through WebSockets. I thought that it's going to be WebSocket. It's actually not. It's a native HTTP functionality. Just set the header. You have a line open, stream stuff to the client. Okay, cool. Then we see the chunks, the HTTP chunks coming in. The first line is size. The second line is the actual content. 2 lines per chunk. Do you notice the first one? It says doc type HTML, right? That is the top of our document, the very first line. And then we see we have the HTML tag open, then we have the head tag, the meta tag, and so on and so on. This is the literal top of the document, right? We do see some underscore next dot push commands or chunks right there. Those are the payloads. That's how Next.js does. Other frameworks do it in a similar way. It's just not called Next. It's going to be something else, right? And what this does is basically it gets all this data. And as you can see, this is how the payload is being sent. There's a couple of hints. There's an I or a module. And this is another line that is the content from the previous chunk. So even even that can be cut into multiple chunks. So this is how the server sends the chunks or the payload to the browser, and this is what the browser literally receives. It parses it, it invokes the next push. That function knows what it's doing. It will put the payload in motion. It will execute it, right? And then we see a red line, and I put it there on purpose. This is the, up until this point, this is the initial page shell. Okay, all of these chunks up until this point, they got sent to the browser in like a few milliseconds. And then this line represents a 5-second chill, wait, and then the browser received 2 more chunks. Those are the chunks that are generated by React for the first suspended component. Okay, because we kept the connection open, we don't care. 5 seconds, we got time, right? The server generates the payload, as you can see, and it's also a $sign payload. That means it's an HTML payload or props payload. It's basically data, not instructions. And then we immediately see an HTML chunk with a little cart there with the number 3. This component basically went into the database and pulled how many items I have in my cart. And we needed to wait 5 seconds for that. Don't ask why. But 5 seconds later, we sent those 2 chunks to the browser. And now the browser used to have a spinner there, but it just replaced that with a cart emoji and 3 at that point, right? And then we wait for a few more seconds later. We got more chunks below the red line. And then we received the closing of the body and HTML tag. So 10 seconds later, the document is still not complete, right? The browser didn't know when the body ends and HTML ends, and yet it still rendered the web page, right? Browsers are resilient. They can render stuff without actually having the document as a complete. That is one of the features that we enable when we set the transfer encoding to chunks. The browser is aware that it's not going to receive the closing of the body and HTML. It's going to receive an incomplete document, but it will still try to render it, right? That's the beauty of it. And then at the end, where that red line is pointing to, there's a 0 and an empty line. That's called a zero-sized chunk. And this is just HTTP. You can do this in Kotlin on the back end if you wanted to. That's called a zero-sized chunk, and that's how the server tells the browser that is the end of the communication, and you can cut the connection at this point because I have no more data to send you. I sent you everything I got. Okay? At that point, the browser received everything. It closed the body and HTML, and we have a document that is fully rendered and hydrated, and it's ready to be used. So that is how the server streams the whole web page asynchronously to the browser. Now let's look at that through a different lens. Now we're going to look at the same payload that I received in the text file, this one, but we're going to look at it through a timeline view in Chrome Performance profile. I'm still going to zoom in. So we're at the very beginning of the timeline. You can see here we're like in less than 85 milliseconds. And of course, I'm running this in dev mode, so it's going to be much faster in production mode. But we can see that the first chunks of HTML are being streamed because this says parse HTML. When you see a blue parse HTML span in the performance profile, that means the browser received some HTML from the server and it's now parsing it, right? And from the initial payload, these ones at the very start, it knows that it needs to pull the layout.css, page.css, and also a font that I'm using, that I'm loading using the next font package, right? We're talking about the 80th millisecond. That's pretty fast. So the browser knows about the CSS. We know that CSS is critical. It's render blocking. It starts to pull it in at the 80th millisecond. So that's good. Then fast forward a few milliseconds later, we can see some JavaScript scripts being loaded. For example, here's the Sentry client configuration for the SDK. This is the next-dev.js for the Next.js dev server. we start to see some JavaScript files being loaded, and we also see a hydrate span right here. Hydration needs to happen before a pixel is put on the screen. I'm not sure about the exact reason why, because we have static data at this point, but that's how it works. At least in Next.js side, they need to do, like the Next.js on the client, on the browser, needs to do a hydration before it starts to render any screens. And there we go. It's hard to see because it's like a white background with a gray gradient, but this is the first frame, the first few pixels of the website being rendered. And we can see that the LCP and FP and FCP are being sent. You want to hack your Lighthouse course? There's the way. You just use RSCs, right? Okay, so after hydration, we saw the first frames coming in. And then 5 seconds later, you see that we're at the 5-second mark at the top. We see another blue parse ML span. Okay, this is that first suspended component, the red line that I showed you in the text file. This is that one through the, this is how Chrome handles it, right? We receive that HTML, we're parsing that HTML, and from that HTML, the browser actually found out that there's a lazy loaded component that it needs to pull. Part of that payload was a bunch of I modules that needs to be pulled, and also HL modules, hints. And so that's why it calls the load style shit, as you can see here. And up here in the network panel, we see 2 requests going to add to car.js, which is a client component if we're loading JavaScript, and also a CSS file, right? So this is true lazy loading. It's not just being loaded when it's needed. Its actual resources like CSS and JS are being fetched when it's needed. Not at the very beginning, but this is at the 5th second, let's say. I mean, I guess people load 5-second websites, but let's just say hypothetically, this is a very big component that gets loaded on the 5th second. If in those 5 seconds I navigate away from the page, my browser doesn't have to load this big component. So I'm going to save up on network, especially if I'm on mobile. That means money, right? So that's good. This is true lazy loading, but this is a hack. I'm going to talk about that in a different way. So there's a hack to truly lazy load client components in Next.js. One thing that you need to see is the DCL event that is being sent after everything is received, right? That means the document, that it stands for document content loaded. That means the browser received that 0 size chunk that I mentioned at the start. There's no more data. It parsed the whole HTML that we received from the browser, and now it says DCL. That's it. The content of the document is loaded, and the connection is closed, and that's it. You can even see this blue bar is the main HTML request. It ends here, and it has a tail up until this point. And then we can see the DCL happening, right? At this point, the browser has all the data that it needs to have for the page, and everything is loaded. But you should have in mind that having the DCL at the 5th second is a bit dangerous. Why? Because if you have libraries or your own code, and you load it as either asynchronous or deferred JavaScript, or a script with a type module, that's going to wait for the DCL. I've noticed some video player libraries, the one that embed the video player on your website, not the HTML native one, but the fancy ones. Some of them load append their scripts as like type module or defer. That means that the user is not going to see a video player for 5 seconds. And if that is the spotlight of your website, the actual content that the user needs to see, if you drag it out to 5 seconds, the DCL, that means you're just deferring. That's why it's defer. You're deferring loading that JavaScript 5 seconds into the timeline. So pay attention to what you're shipping to the browser, because if you have type module or asynchronous or deferred scripts, they're going to load much later. They're not going to be loaded. Even though the browser will receive their JavaScript, it's just not going to bother invoking that JavaScript unless the DCL happens. So keep that in mind because I've made some mistakes and I've learned that. All right, so we're going to see two screenshots of Sentry that show performance differences between a traditional SSR and RSCs. This is the same demo app that I built. I just switched over to Pages router, so it's fully SSR rendered the traditional way. And then I also refactored it with the app router, so it uses RSCs, so it's the new thing. And the performance differences are night and day. I mean, look at this. Page router, traditional SSR on the left, all of the web vitals are 4+ seconds. Why? Because that's how long the application took to gather the data and send everything back to the server. That is the first byte that the browser received, so everything is going to be 4+ seconds, right? And you see Sentry is giving you the red flame here to tell you need to do something about this, right? But on the other hand, we see the RSC is up. It's like 176 milliseconds. The time to first byte is 152. That's pretty good, right? We don't need to wait for the data. The first data that the browser received was like 150 milliseconds after it initiated the request, which is pretty good, right? And this is why it happens. I zoomed in on this one pretty hard, so you can see, but the first bar that says 4 seconds, that's the main request. The second little line right here, that's the response. All right, that's how long the server took to respond back to the browser with all the data, this is traditional SSR, right? And then the yellow lines and bars, these are resources. HTML, CSS, JavaScript files that the browser pulls. But it finds out about these resources when it gets the word back from the server, which is 4 seconds after initiating the request. Whereas in the RSC's case, the top blue bar is the request, the second blue bar is the response. All right, this is the tiny blue line that we saw. In this case, it's much longer because the connection is, kept open. But this allows the server to tell the browser, pull all of these resources in advance. And you see, this little line indicates that there's an event being marked there, which is most likely one of the web vitals. So the differences are night and day, as you can see. This is the performance boost that we get just by refactoring from traditional Pages router to RSCs. We get to tell the browser this is what's going to be on this website in like 150 milliseconds later. You can't beat that, right? So it was overwhelming, I know, forensics and stuff. So let's do a quick recap just so we, hold on to this knowledge. RSCs is a new architecture by React that leverages the good parts of client-side rendering and server-side rendering and implements streaming so it can allow us to send the data to the browser as soon as possible and then defer any heavy or slow loading components for later. But let the browser draw the website or paint the website first. It introduced two new components, server components and client components. We learned that server components are the default type of components unless we really need to handle any interactions, then we refactor them into client components or isolate that specific functionality into its own client component. It has its own challenges. First, we need to rethink how we architect our application because it does change the way that we structure the UI tree a bit, right? If we're doing CSR, we don't care about this. We'll just import one component into another. But with the relationship between server components and client components and the fact that you can't explicitly import a server component into a client component will make you stop and rethink how you're approaching or architecting your front end in this case. But yeah, it has its own challenges, but overall, we saw that there are significant performance improvements when it comes to rendering the web page and the ability for the users to not wait for the whole content to load if they want to see some parts of the content of it. So yeah, Thank you. This was overwhelming, but yeah, awesome. Yeah. Thank you. If you want to check out how Sentry works, there's like a little sandbox. You can go and check it out. There's no sign up, no credit cards, anything. But yeah, do we go into Q&A now, right?
Yeah, I would say like about 5 to 10 minutes of questions, otherwise
Yeah.
it'd be too long.
Okay. Yeah. Awesome. Thanks.
I have a question. So about the architecture you mentioned at the end, and going back to the family tree diagram.
Okay.
So it just kind of got me wondering. So once you have a child component, are you basically expected to have children client component after that? Or at least if one of the client component has a child.
In the perfect scenario, you don't, right? I do have it here to indicate that you can have child components that are client components of other client components, but React wants us to just isolate only that specific functionality into its own component. See, I have a button input. There's a form with validation here. So I need JavaScript if I want to use Zod, right? But we have static widgets. We have a page. We have a footer. We have a navbar. All of that is going to be server component, except for these, right? So as you can see, input button, if we have like interactive elements, usually they don't have child components.
So ideally,
Yeah.
design it in a way so that you shouldn't have any.
Yeah, like in this case, I have a form. I need it to be client component because I'm using Zot, and that will have children, and those will still be client components. But if we try to put a server component in this case, that's when we're gonna see some errors popping up. But in like perfect scenario, right? We're going to isolate that, just like the button, or just even like turn it into a hook, and just send the hook. But yeah.
Thank you.
So we need to get them as a child, as an argument to other component, the server component.
Sorry, can you repeat that?
I was going to ask the same question. So we need to get the client component to the server component as a child, as an argument.
Yeah, we can import client components into server components, but not the other way around. We can't like import component from server component. That's going to be a client component, even if the file is called server component.
Same thing.
Yeah. Yep.
So your example of the slow version, 5 seconds,
Uh-huh.
that's very slow. So
Very slow.
So,
It's a timeout.
but normally, if you do nothing, it should be pretty fast, right?
Yeah.
It only gets slow when you start using, database on it.
Mhm.
But if I'm in a situation where something takes 5 seconds, I can also just not do that in line and just do a query on the side and just as a separate HTTP request. And that's like very easy to do versus switching to completely new architecture.
Mhm.
So how do you decide what to do? Because I feel like you need more than just one slow page to
Yeah.
adopt this kind of stuff.
Yeah. Well, in that case, you're going to need to pull the server from the client. That can also mean we send a request and the server says it's not ready yet. Then we send another one, it's not ready yet, right? So I think with this setup, the RSCs, that's kind of built in, and it takes away the responsibility of you to handle the polling, and handle the retries, and handle the responses back from the server. It basically hides away all of that, so you can. It's good for DX, right? So you don't need to implement additional fetches, or take the WebSocket route. The data is ready. Okay, give it to me. So I guess that's like at least you have better DX, and it's automatic, right? Yeah.
How do you design for security differently if you have server components or a hybrid?
If we have
Some server components, some client components, or a mixture, how do you design for security differently or think of it?
well, just look at the component, right? If the component is a client component, you'll be aware that everything that you do in there will get sent to the browser, right? So you can use props. You can do sensitive stuff or use sensitive tools or API keys in the parent server component, get the result, and then send the result as like a prop to the client component. So only the result gets sent to the browser, but not the API key or the library that we're using on the server. Props are one way to go. Yeah. Context is a different beast in this case, and that is one of the methods that you're going to see server components inside client components through the children prop, because you know React context needs to live on the client, and you need to set that as a client component. And usually the context is defined at the like the lowest possible level where the components need to use it. Some of them are like at the top of the page. So you would have client components that define React contexts and accept children, which are going to be server components. And that's fine. That's why I mentioned that you can pass a server component into a child component, but only through the children prop. Because at build time, React knows that it's the relationship is like through the children prop, so it's going to still consider this as a server component. Whereas if you use the import keyword and point to a server component in a client component, that's when you're pulling in modules. So it will treat the server component differently.
One more question.
Yeah?
No, I'm saying like final question.
Final question. All right. Yeah.
So the RSC payload which was passed to the browser, so how does the browser recognize that payload? I mean, like recognizing a JSON payload is fine,
Yeah.
but how does it recognize a special, like a special sort of a?
It's a string.
Okay.
It's literally a string. Look at this. See? So the server sends a string in a specific format where it says the first few characters are this. Then we have this character. Then we have this character, right? So it has a specific format that the browser, not the browser, the browser doesn't understand. It's a string. The library needs it. Here, go ahead. Knock yourself out. But the React knows about this. Let me try to find the other slide where this one. Check it out. Self.next.push. You have an array. The first element is a number. It always is a number. I don't know what it stands for. It's not documented. But the actual payload is a string. And then when we have a quotation inside, you see that we're escaping that quote. So it can be treated as a string within a string, right? So the payload is sent as a string, well, like the content of the payload. But the instruction on how to load the payload is the next.push command right there. Yeah, awesome. It's a good question. Thanks, y'all.
All right, guys.